Okay. Yeah, I don't want to talk too long. It's just to give you very quick guidance. I mean, I hope that the documentation which you find on GitHub. So if on GitHub you go here, so that's the HiQ training, and you go into HPC, and then hands-on, you should find here then Poisson 2D. I hope you all found it.
What's the GitHub address?
GitHub.com/haiku.
Yeah, could you just post it in the chat?
Yeah, I do.
Are you joining Zoom as well? Okay. Actually, just you can see it on top. Maybe you can remove the screen. If you just move the button, I think then you can see it.
Yeah, it somehow doesn't seem that this part goes away.
On more, you can click on hide. Yeah.
Ah, okay.
It's on more. Click on more.
Yeah, this one. Can you see it now?
You can hide this one here. You can hide that view.
Hide floating, hide. Yeah, I can see the address on top. All right.
Okay. Yeah, for the next time I would recommend then also putting a Slack channel in place. Then,
yes.
yeah, that is sometimes a bit more convenient than using or just getting on Zoom for the chat, just for the purpose of the chat. Okay. Did everybody here on site manage to get to the Git repository? So, what is there is, oops, here on the page itself, is you can find here, say, a bit of, say, documentation which was already shown before in the slides. So you find essentially the same pictures back there. And now the one thing which I didn't explain, say, earlier today, because the focus was just on a particular computational pattern, is that since we have in the lecture, we got to the point that we said, okay, I mean, we are, say, having here to deal with, say, an equation which we want to solve, where the matrix has a feature that it's what is called diagonal dominant. That means that the diagonal elements are, say, significantly larger, and the factor 4 is already, say, numerically sufficient to make it significantly larger. So this is called a diagonally dominant matrix. And there is a method on how to solve that numerically, and that is called the Jacobi method. Sorry, I was clicking the wrong button. So essentially you can, say, write this matrix in two parts. So you have D, which is thus containing, say, the diagonal elements, and then you have here the off-diagonal elements. And the Jacobi algorithm is essentially an iterative procedure for obtaining the solution by, say, having the following iteration. So you start with one proposal for, say, a solution vector V. And now you apply basically here this right-hand side to construct a new proposal for the solution. And because of the property of this being, say, diagonally dominant, you have, say, a guarantee for this to converge. May not necessarily converge very efficiently, but this is now it's not saying about, say, numerics here. Now, the nice thing here is, I mean, while we have here the inverse of a matrix, but it's the inverse of a diagonal matrix, which is trivial to compute, right? So it's easy to compute this one, and for the off-diagonal part, we only have multiplication with the off-diagonal matrix, right? So, and that is what is a nice property. Now, again, we are writing this as a matrix equation, and that's how you do it, that's how you basically write it mathematically. Obviously, because most of the elements of R are 0, right? because not only the diagonal elements, but most of the off-diagonal elements are 0. You will never say explicitly write R as a matrix, right? Even so, you could, in principle, do it. And that's where basically it becomes about the stencil computation. Now, let's briefly have a look in, depending on whether you are a C programmer or a Fortran programmer, sorry, I'm now just looking into the C implementation. That is here the main function. And if you want to influence it, I try to have a very simple implementation. It's basically of C preprocessor variables, which defines, for instance, the size of the two-dimensional grid and what is actually also the stopping criterion. So when, how precise is the solution, should the solution be? And then we just have here the main is just initializing F, but then at some point the solver is being called. And the solver is being put into a different file. And you can find here, this is a vanilla implementation. And so what you can see here is that here you have a loop which says, okay, while the error is larger than, say, a stopping criterion, or while we have, we have not done, say, not done too many iterations. So that is also what you often do with iterative solvers. You don't allow it to iterate for infinite, because just even if it's guaranteed to converge, you might have put here a too small limit here, and then it might numerically never converge, for instance, due to rounding errors. So that's why it's quite a standard way of looking, okay, I iterate as long as my error is still too big, or as long as I haven't done too many iterations, right? And that, of course, would be an error case. Now, what I do here is essentially here, I compute now a new value called here V prime. That is now the new value of V. And this is essentially taking, it's not too difficult. I would just suggest to look at a bit of a pen and paper exercise. Then you can see it essentially, say, according to this procedure for the Jacobi iteration. And here you have, say, the off-diagonal elements. And you can see here we explicitly compute, basically, the neighbors, right? So we don't have a neighbor list. You could do it, but it would obviously be not particularly efficient. And what at the end we do here is also we compute now, say, the error, and this determines of when, say, the iteration, say, converges. So I hope it's not too difficult to understand of what the application is actually doing. And then it's up to you of how quickly you can, say, get to hands-on, also where you would like to focus on. So one thing could be, for instance, to use the performance tools to try to understand of what is the performance critical region. That should be, say, pretty trivial. If you like to exercise more some of the things which we went through with, for instance, the roofline model, I think it's not too difficult case to actually compute the arithmetic intensity. So, and then it's now, say, the next step would be to actually try to look a bit in what is actually the performance which one observes, right? So once you have gone through the exercise of computing the arithmetic intensity, you can start of making, say, an estimate of how much performance would you actually, say, expect, and how much off am I in this expectation. And for instance, look also into what are the spatial and temporal data locality properties. And then you can start to look at the code and for instance, either, say, by theoretical thinking, look what is easy ways to optimize this code based on what we learned. but maybe also look into, say, the tools and for instance, look at the level 1 cache misses. You can either instrument the code with PAPI, or you can also use Scalaska. So, I mean, it's also the goal of, say, getting some exercise with just using the tools, right? But it's a bit up to you in making a decision on what is the thing I want to focus on, say, given the amount of time which is left till basically the end of the day, on where you would think for you would get most benefit. Is it mainly to practice with the tools? Is it mainly also to practice some of this theoretical, say, ways of analyzing, say, applications? And then to check whether, say, what I think is theoretically correct, then actually look at the architecture on whether this actually works. Right? And then if you have even some background here, I mean, we didn't talk about parallelizing this application here, but of course, something which is certainly not too difficult is, for instance, also to think about, for those who had in the past, for instance, looked at parallelizing using OpenMP. That should be, say, rather straightforward to actually also try to parallelize it with OpenMP. So if you have some background in OpenMP, then you can, for instance, start to look in how does performance change on this given processor architecture when I start to use multi-threading for this particular case. So there's a number of directions where you can go. My recommendation is maybe start, say, first getting it compiled, familiarize a bit with the performance tools. And then once you have achieved that, then maybe start to think either go more in the direction of just computing arithmetic intensity and try to see, okay, do I understand the performance figures which I see? Or alternatively also to endeavor a bit on say, speeding up things, a bit more a black box approach and using, for instance, OpenMP to parallelize it. Yeah, any questions on that so far? Okay, then I wish you fun with doing that, and yeah, I hope it's you should now have all the address. It's probably not too populated, so probably cloning the full Git repository. Then you have automatically also a copy of the. So all the slides which I have been presenting so far, they're also in the same repository. So if you do a checkout of the full repository, then you have automatically a copy of the slides. Both my slides as well as Stepan's slides on local as a local copy.
Yeah, I think I sent the link for the lectures on the chat. If there is any questions, we can please let us know. Otherwise, we can go into the breakout rooms. I have left it to you to decide which room you want to go, and then please assign yourself so that you are balanced across the rooms. Yeah, thank you.